In this session, we discuss what are congruence classes. Earlier, we have seen that the congruence relation defined on the set of integers is an equivalence relation. That is, the relation defined on set by A congruent to B mod M, we call it actually the congruence modulo M relation. The congruence modulo M relation is reflexive. That is, for every A in set, A is congruent to A modulo M. Secondly, the symmetric, that is, for any AB in set, A congruent to B mod M, if and only if B congruent to A mod M, and it is transitive, that is, for any A, B, C in set, if A congruent to B mod M and B congruent to C mod M, then A congruent to C mod M. That is, the congruence modulo M relation defined on the set of integers is reflexive, symmetric and transitive, and hence it is an equivalence relation. Any equivalence relation defined on a set, suppose R is an equivalence relation defined on a set S, then this relation will partition the set into equivalence classes, which are nothing but the disjoint subsets of S. Here, the congruence relation partition the set of integers into finite number of disjoint subsets, and these subsets are called congruence classes. For example, let us take M is equal to 5. Then you consider the congruence modulo 5 relation on set of integers. That is, A congruent to B mod 5 relation defined on set of integers. We say A is related to B when only if A is congruent to B mod 5. Now this congruence relation on set of integers will generate disjoint subsets of set in such a way that they are represented by 0, 1, 2, 3 and 4, where 0 is the set of integers which are divisible by M. That is, those integers which are congruent to 0 modulo 5, which leaves the remainder 0 when divided by 5. Such integers are multiples of 5. So 0, 5, 10, etc. Similarly, minus 5, minus 10 to the left side. these integers are actually multiples of 5 or they leave the remainder 0 when divided by 5. And this is one such a subset we are getting, that is the congruence class. Another congruence class is 1, which is all the integers which leave the remainder 1. Those integers a which leave the remainder 1 when divided by 5. So they are nothing but minus 9, minus 4, 1, 6, 11, etc., which can be written very easily by adding 1 to all these elements in 0. Now this third class is those integers which leave the remainder 2 when divided by 5. That is those integers which are congruent to modulo 5. So the numbers are minus 8, etc., minus 8, minus 3, 2, 7, 12, etc. The congruence class 3 is those integers which leave the remainder 3 when divided by 5. They are minus 7, etc., minus 7, etc., minus 7, then minus 2, then 3, 8, 13, etc. And 4 is those integers which leave the remainder 4 when divided by 5. They are the numbers like minus 6, minus 3, 2, 9, 14, etc. These sets 0, 1, 2, 3 and 4, they are subsets of X, disjoint subsets of Z, and whose union is actually the set of integers, is the set of congruence classes modulo 5. Modulo 5. Let us take M, another example. M is equal to 7. So find all the congruence modulo 5 classes. Congruence class modulo 5. Congruence class modulo 5. Here the relation is A congruent to B mode 7. This is mode 5 and this is mode 7. So whenever A is congruent to B mode 7, we say A is related to B, and this is an equivalence relation, and this generates actually congruence classes modulo 7. They are 0, 1, 2, 3, 4, 5 and 6. And 6. And remember, this 0 is different from the previous 0. Here the 0 is the congruence class when consisting of the integers which leave the remainder 0 when divided by 5. Here this 0 means those integers which leave the remainder 0 when divided by 7, on division by 7. Those integers A which are congruent to 0 mode 7. So 0 consists of all the integers like minus 7, 0, 7, 14, etc., which are multiples of 7. Congruence class 1 it consists of all the integers like minus 6, 1, 8, 15, etc. 3, 2 consists of all the integers like 2, 9, 16, etc. minus 5, minus 12, etc. 3 consists of the integers like minus 11, minus 4, 3, 10, 17, etc. which leave the remainder 3 when divided by 7. 4 consists of all the integers like minus 10, minus 3, then 4, 11, 18, etc. 5 consists of the integers minus 9, minus 2, that is minus 2, then 5, 12, 19, etc. Then finally the last class is those integers which leave the remainder 6, which are nothing but minus 8, minus 3, minus 1, then 6, 13, 20, etc. Thus the congruence classes modulo 7 are 0, 1, 2, 3, 4, 5 and 6. Now we define a new concept or a term called a complete set of residue modulo M. A complete set of residue modulo M. Modulo M. Modulo M. A complete set of residues modulo M. Now what is this? Let us see. It is a set of m integers. For example, set a1, a2, a3, etc. am. A set of m integers is said to be a complete set of residues modulo m if these integers a, I are actually congruent to one of the residues 0, 1, 2, etc. m minus 1. Say I am writing some j modulo m, where j belongs to either 0, 1, 2, etc. m minus 1. And for any I, there exists a unique j. If I is different, you will get another j. If I you are taking 2, for example, a2 is congruent to one of these integers modulo m. a3 is congruent to one of another integers modulo m. This way, if they are congruent modulo m to the least residue 0, 1, 2, etc. m minus 1 in some order. So the set of integers a1, a2, etc. am is said to be a complete set of residue modulo m, is a complete set of residue modulo m if they are, these integers are congruent modulo m to the least residues 0, 1, 2, etc. m minus 1 in some order. So there are m integers and this is a complete set of residues modulo m if they are congruent modulo m to the least residue 0, 1, 2, etc. m minus 1 in some order. Let us take an example. Consider the set example, consider the set minus 12, 9, 6, 23. It is a complete set of residue modulo 4. Residue modulo 4. There are 4 integers here. So, it is a complete set of residue modulo 4. That means minus 12 is congruent to one integer like 0, 1, 2, 3. 9 is congruent to one of these integers 0, 1, 2, 3. 6 is congruent to one of these integers modulo 4, and 23 is also congruent to another integer in the set modulo 4. We know minus 12 is congruent to 0 mod 4 because minus 12 minus 0 is divisible by 4. 9 is congruent to 1 modulo 4 because 9 minus 1 is 8, which is divisible by 4. 6 is congruent to 2 modulo 4 and 23 is congruent to 3 modulo 4. So, minus 12, 9, 6, 23, these integers form a set which is a complete set of residues modulo m, since these integers are congruent modulo 4 to one of these 0, 1, 2, 3 in some order. Such a set of integers is called a complete set of residue modulo 4. Now we discuss some more results here. It's a theorem. Let A congruent to B mod M, C congruent to D mod M, then we have A plus C congruent to B plus D mod M, AC congruent to BD mod M. So, if we have two congruence relations like A congruent to B mod M, C congruent to D mod M, then they can be added and they can be multiplied like this: A plus C congruent to B plus D mod M, AC congruent to BD mod M. Proof is very simple. We want to show A plus C is congruent to B plus D mod M. So, it is enough to show M divides A plus C minus B plus D. Here given proof of 1, given A is congruent to B mod M and C is congruent to D mod M. That is given M divides A minus B and M divides C minus D. And therefore, it is very clear that M divides A minus B plus C minus D. That is, M divides, when you add this is nothing but A plus C minus B plus D, and which shows that A plus C is congruent to B plus D mod M. So, if A is congruent to B mod M, C is congruent to D mod M, then it is very clear A plus C is congruent to B plus D mod M. Secondly, we have to prove AC congruent to BD mod M. For that, we have to prove M divides AC minus BD with the condition M divides A minus B and M divides C minus D. Or you have to prove AC minus BD is a multiple of M. The proof of 2 goes like this: AC minus BD you can write as AC minus BC plus BC minus BD. This is another way we are proving. The same way also we can prove if we just take the product of A minus B and C minus D. That way also you can prove. AC minus BD, you have to show it is a multiple of M. AC minus BD you can write as AC minus BC by adding and subtracting. And this is, you can write as C into A minus B plus B into C minus D. Now, A minus B is a multiple of M. Therefore, A minus B is nothing but some LM. For C into some LM. Because A minus B is a multiple of M. M divides A minus B, which means, this implies A minus B you can write as some LM. Similarly, C minus D is some Km, because C minus D is a multiple of M. Therefore, C minus D is Km. So, C into Lm plus B into C minus D is some Km. And therefore, you can write this M into Cl plus Bk. So, the right side is nothing but a multiple of M. That is, C into A minus B plus B into C minus D is a multiple of M. And therefore, M divides AC minus BD. This implies AC is congruent to BD mod M. That's the result. So, this result shows that if A congruent to B mod M and C is congruent to D mod M, then we can add A plus C congruent to B plus D mod M and AC congruent to B D mod M. So, let us see some example of this type. For example, we know 8 is congruent to 3 mod 5. 13 is congruent to, or let it be 14. 14 is congruent to 4 mod 5. So, adding, what do we get? 8 plus 14. But it is very clear that it is, we are expecting this 18 plus 14 is congruent to 3 plus 4 mod 5 as per that rule. So, let us check whether it is right or not. 18 plus 14 is 22, is clearly congruent to 7 mod 5. So, this is, since 22 is congruent to 7 mod 5, 8 plus 14 is congruent to 3 plus 4 mod 5. So, hence it is verified. Similarly, if you multiply, we are expecting 8 into 14 should be congruent to 3 into 4 mod 5. So, this also you can verify. The reason is 8 into 14, it is 112. Is clearly congruent to 3 into 4, 12 mod 5. Mod 5. Because 112 minus 12, 100 divisible by 5. And therefore, 8 into 14 is congruent to 3 into 4 mod 5. Now, let us do one important problem here using this idea. Find the remainder. When 1 factorial plus 2 factorial plus 3 factorial plus etc. plus 100 factorial is divided by 50. Is divided by 15. We have to find the remainder when divided by 50. 1 factorial plus 2 factorial plus etc. 100 factorial. When it is divided by 15, what will be the remainder? That is what we have to find. By a little observation, we can see that some k factorial, if you take, because all the terms are of this type k factorial, where k is equal to 1, 2, 3, etc. 100. So any term is of the type k factorial. If k is clearly greater than or equal to 5, if k, suppose it is 5 or 6 or 7, then this k factorial will definitely have factors 1, 2, 3, 4, 5. Definitely it will be there. If you suppose it is 7 we are taking, then it is 1, 2, 3, 4, 5, 6, 7. Or if you take 6, 1, 2, 3, 4, 5, 6 will be there. 5 factorial if you take. So these terms will be the factors if k greater than or equal to 5. That means every k factorial contains 3 and 5 as a product. That is 15 is a factor of k factorial. That means for every k greater than or equal to 5, 15 divides k factorial. Or in other words, we can say that k factorial is congruent to 0 mod 15. So this is the result what we are getting through this observation. For every k greater than or equal to 5, that k factorial is congruent to 0 mod 15. We want to find the remainder when this number 1 factorial plus etc. 100 factorial is divided by 50. That means we want to find what is r such that 1 factorial plus 2 factorial plus 3 factorial plus etc. plus 100 factorial is congruent to r mod 50. We have to find that r. This r, we are expecting 0 less than or equal to r less than 50. We have to find an r in between 0 and 15. That is greater than or equal to 0 and less than 15, satisfying this congruence relation. Now, how do we find? It is very easy. 1 factorial plus 2 factorial plus 3 factorial plus etc. Let us take up to 4 factorial. Then 5 factorial plus etc. 100 factorial is clearly congruent. All these 4 factorial, 5 factorial onwards, that is 5 factorial, 6 factorial etc. 100 factorial are congruent. This is actually for all k greater than or equal to 5. So this 5 factorial is congruent to 0 mod 15. So we have 5 factorial is congruent to 0 mod 15. 6 factorial is clearly congruent to 0 mod 15, etc. 100 factorial is also congruent to 0 mod 15. And therefore, this is congruent to 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial. But the terms after that all are congruent to 0 mod 15 plus etc. 0 mod 15. Mod 15. From these terms onwards, 5 factorial plus etc. plus 100 factorial are congruent to 0 mod 15. And therefore, this is congruent to only 1 factorial, that is 1 plus, 2 factorial, that is 2 plus, 3 factorial, 6 plus, 4 factorial, 24, plus 0 means only this, mod 15. And that is congruent to 1 plus 2, 3 plus 6, 9 plus 24, 33, 33 congruent to mod 15. Congruent to 33 mod 15. And this is clearly congruent to 30 plus 3. This is actually congruent to 30 plus 3 mod 15. But 30 is congruent to 0 mode 50, and therefore it is only 0 plus 3 mode 15. 0 plus 3 mode 15, which is congruent to 3 mode 50. Thus, the left side 1 factorial plus 2 factorial plus etc. plus 100 factorial is congruent to 3 mode 50, and therefore the remainder is equal to 3 on dividing the left side sigma n factorial where n equal to 1 to 100 by 50. Now another problem is find the positive integer n. Find the positive integer n for which sigma k factorial k is equal to 1 to n is a square. So here we want to find for what value of n. For example, 1 factorial plus 2 factorial plus etc. plus n factorial becomes a square. We know 1 factorial, that is 1, that is a square. Whereas 1 factorial plus 2 factorial, we know it is 3, it is not a square. 1 factorial plus 2 factorial plus 3 factorial, again it is not a square. So we have to identify the values of n. For what values, positive integers n, for which this summation is a square. Here also we know for any k greater than or equal to 5, k factorial is congruent to 0 mode 10. 0 mode 10. Because if you take at least k is equal to 5, k factorial consists of 1 into 2 into 3 into 4 into 5. So there is a product 2 into 5 there, that is 10. So k factorial is a multiple of 10 for all k greater than or equal to 5. If you take k is equal to 6, then k factorial is equal to 1 into 2 into 3 into 4 into 5 into 6. There also there is a product 2 into 5, 10. So for every k greater than or equal to 5, k factorial is congruent to 0 mode 10. 0 mode 10 means if you find the k factorial, it is actually a multiple of 10. K factorial is a multiple of 10. And therefore, what is the remainder when k factorial is divided by 10? Let us find first that. What is the remainder when k factorial is divided by 10? Sigma k is equal to 110, k factorial is divided by 10. So that is the number we have. So let n is equal to sigma k factorial, k is equal to 1 to n. Then n is 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial plus 6 factorial plus etc. plus n factorial. Now for all k greater than or equal to 5, every factorial, k factorial is congruent to 0 mode 10. Therefore, it is congruent to 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 0 plus etc. plus 0 mode 10. Because all these 5 factorial, 6 factorial etc. are congruent to 0 mode 10. So that is congruent to, again here if you compute this, we get 33 as we saw earlier, 33 mode 10 So 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial is 33. So it is congruent to 33 mod 10. And as we written earlier, 33 is 30 plus 3 and 30 is divisible by 10. Therefore, it is congruent to 3 mod 10. 3 mod 10. That means this n, when it is divided by 10, you are getting the remainder as 3. Which shows that the unit place, the digits in the unit place is 3. Because we have a number like 253. When it is divided by 10, it leaves the remainder 3. And therefore 3 is the, if it leaves the remainder 3, 3 will be in the unit place. So here n, when we compute the digit in the unit place of n is 3. Now, what number which ends in 3 can be a square? You have to check. What number, say for example m, can this m square be an integer which ends in 3? Or you have to find out m square congruent to 3 mod 10. What are the integers like 0, 1, 2, 3, etc., 9, whose squares congruent to 3 mod 10? Because we are expecting for what value of n? This sigma k factorial, n k is equal to 1 to n is a square. That is, this n is a square. So for this n to be a square, since n is the digit in the unit place is 3, what number if you take, whose square can be this n? So for that, any number if you take, it should be either ends in 0, 1, 2, 3 up to 9. Which of these digits can be in the unit place whose square, when it is divided by 10, leaves the remainder 3? So what about 0? Let us 0 square, we know it is congruent to 0 mod 10. 0 mod 10. So it never ends in 3. 1 square is congruent to 1 mod 10. We know. 2 square is congruent to, that is 4. That is, if any integer that ends in 2, whose square will be ending in 4. So 2 square is congruent to 4 mod 10. 3 square is congruent to 9 mod 10. 4 square is congruent to 6 mod 10. Because 4 square is 16. 5 square is congruent to 5 mod 10. Because 5 square is 25 and it is divided by 10, leaves the remainder 5. 6 square is congruent to 6 mod 10. 7 square is congruent again 9 mod 10. 8 square is congruent to 4 mod 10. 9 square is congruent to 1 mod 10, because 9 square is 81. Consequently, the square of every integer, if you take, it is either ending in 0. So the integer whose square ends in either 0, 1, 4, 5, 6 or 9. Any number if you take whose square is ending in only in 0, 1, 4, 5, 6, 9. For example, if you take 253 square, if you take, then it ends in 9. So whatever number integer if you take, whose squares if you take, that end in 0, 1, 4, 5, 6, 9 only. And therefore, here we want, since this capital N, the given number n, sigma k factorial n equal to 1 to n, ends in 3 for every n. It cannot be these integers 0, 1, 4, 5, 6, 9. So what does it show? When n equal to 1, we can say sigma k factorial k is equal to 1 to n is only 1, and therefore it is a perfect square. When n equal to 3, n equal to 3, what is n? Sigma k factorial k is equal to 1 to 3, which is 1 factorial plus 2 factorial plus 3 factorial, which is 9, and that is a perfect square. So when n is equal to 1, this is a perfect square. When n equal to 3, it is a perfect square. When n equal to 2 or 4, they are not a perfect squares. So there are only two positive integers n for which sigma k factorial can be a perfect square. They are 1 and 3. Only for n is equal to 1 and 3, this sigma k factorial can be a square. Because if you take any other k whose squares either end in 0, 1, 4, 5, 6, 9. But here we calculated n is for k greater than or equal to 5. For k greater than or equal to 5, if you calculate sigma k factorial, the remainder is 3 only. And therefore, it is possible that for 1, 2, 3, 4, sigma k factorial can be a square, but we checked one by one. For n equal to 1, it is sigma k factorial is 1, it is a perfect square. For n equal to 3, it is a perfect square because sigma k factorial is 9, but for 2 and 4, it is not a perfect square. We can compute. For n is equal to 2, sigma k factorial is 1 factorial plus 2 factorial, which is 3, not a perfect square. When n is equal to 4, sigma k factorial is equal to 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial. 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial. You can see that it is not a perfect square. It is also not a perfect square. So the only possibility for n equal to 1 and 3, the sigma k factorial is a perfect square. So we saw that if A is congruent to B mod M and C is congruent to D mod M, then A plus C is congruent to B plus D mod M. Similarly, we can easily show A minus C is also congruent to B minus D mod M. This is because we have another result here. AC is congruent to BD mod M. We have minus 1 is congruent to minus 1 mod M. Therefore, using this and this relation, minus C is congruent to minus D mod M. So by adding this 1 and 2, we'll have a minus c congruent to b minus c mode m. A minus c congruent to b minus d. If c is congruent to d mod m, then we have minus c is congruent to minus d mod m, and therefore adding 1 and 2, we get a minus c is congruent to b minus d mod. So this is also another relation. Now another result, this is some result one we are getting from the previous two results. Then another result is corollary, we can say, if A is congruent to B mod m and C is any integer, then you can multiply on both sides by C. AC is congruent to BC mod m. So this result is A is congruent to C mod m implies AC, so A congruent to B mod m implies AC congruent to BC mod m. Proof is very simple, because A congruent to B mod m means proof A congruent to B mod m implies m divides a minus b. Therefore it is very clear that m divides some c into a minus b, that is m divides ac minus bc, which implies ac congruent to bc mod m. For example, if you take, we know 8 is congruent to 3 mod 5. You multiply by some number 4, for example. Let C be 4. So we are expecting 8 into 4 is congruent to 3 into 4 mod 5. We can check whether it is right or not. Clearly 8 into 4 is 32. 3 into 4 is 12. Clearly 32 is congruent to 12 mod 5. 32 minus 12 is 20, is divisible by 5. So this is right, and therefore this is verified. 8 into 4 is congruent to 3 into 4 mod 5. Now here we have to understand another concept. If AC congruent to BC mod m, does it imply by cancelling C, can you write this A congruent to B mod m? If AC is congruent to BC mod m, suppose you are cancelling this C, will it imply A congruent to B mod m? We will be seeing later that it is not. You cannot divide a common factor here, say C. This relation will not hold. This relation will hold only if C and M are relatively prime. So that is discussed as another theorem later. Now another result is, if A is congruent to B mod m and C is any integer, then we have A plus C congruent to B plus C mod m. You can add same number C on the both sides. You can subtract same number from both sides, still the congruence relation hold. That is A minus C is congruent to B minus C mod m. You can multiply both sides by the same number integer, that is you get AC congruent to BC modium. And another result that we are getting is, if A is congruent to B modium, then A square is congruent to B square modium. That is also holding. All this you can verify easily. The last result we can check. If A is congruent to B modium, you take A is congruent to B modium again. Now we have the relation, if A is congruent to B modium and C is congruent to D modium, then AC is congruent to BD modium. So by multiplying, A into A is congruent to B into B modium. That is, A square is congruent to B square mod M. In general, this 4 can be generalized as a theorem that if A congruent to B mod M, then A raised n is congruent to B raised n mod M for any integer n. Clearly, for n equal to 2, we already verified. For n is equal to 2, we have seen that A is congruent to B modium implies A square is congruent to B square mod M. We are proving this by some induction. Suppose for n is equal to k, it is true. Let for n equal to k, this be true. That means A congruent to B modium implies A raised to k congruent to B raised to k modium. Then multiplying by A on both sides, we get A into A raised to k is congruent to B into B raised to k mod M, which implies A raised to k plus 1 is congruent to B raised to k plus 1 mod M. Thus, for every integer by induction method, for all n, A raised n is congruent to B raised n mod M. So that is the proof of this. Using this, let us do a problem of finding the remainder when A raised n is divided by some number. For example, you take the problem like this. Find the remainder when when 16 raised to 53 is divided by 7. We know it is done like this. 16 is clearly congruent to 2 mod 7. 16 is congruent to 2 mod 7. Here we want to find 16 raised to 53. So we have the relation that if A is congruent to B mod M, this implies A raised n is congruent to B raised n mod M for any integer. And therefore, 16 raised to 53 is congruent to 2 raised to 53 mod 7. We want to find actually when 2 raised to 16 raised to 53, the remainder when 16 raised to 53 divided by 7. So here it is now reduced to 2 raised to 53. If you can find the remainder when 2 raised to 53 divided by 7, the same remainder will be the remainder when 16 raised to 53 divided by, because they are congruent. And it is easy to calculate 2 raised to 50, easier. It is easier to calculate the remainder 2 raised to 53 when divided by 7. Now 2 raised to 53. How do you find the remainder when divided by 7? We know 2 raised to 3 is clearly congruent to 1 mod 7, because 2 raised to 3 is 8. So if we can write 2 raised to 53 in terms of 2 raised to 3, powers of 2 raised to 3, it is very easy to find. For that, 53 you can write as 3 into 17 plus 1 we have. Therefore 2 raised to 53 you can write as 2 raised to 3 into 17 plus 1 modulo 7. It is congruent to 2 raised to 3 raised to 17, that is 2 raised to 3 into 17 plus 1 you can write into 2 mod 7. But 2 raised to 3 is congruent to 1 mod 7. So this is congruent to 1 raised to 17 into 2 mod 7. And that is congruent to 1 raised to 17 is 1, 1 into 2 is 2, 2 mod 7. So easily we got the remainder when 2 raised to 53 divided by 7 this way. So as far as possible, you have to write this is number is congruent to 1 modulo m, so that its power 1 raised to n is always 1. So it is very easy to calculate. So that is the idea behind this. First of all, 16 raised to 53, that base number 16 is reduced to a smaller number 2. Again that 2 is reduced to smaller number 1 here. So this way we can find the remainder when some a raised to n divided by m. So this type of problem you can practice. So with this I conclude this session. Thank you.